So another very common calculation that we're going to be doing in chemistry is to calculate the reaction yield. And the reaction yield is sometimes given in grams, sometimes given in moles, but most commonly it's given as a percentage of the theoretically possible reaction yield. So we're going to learn how to calculate all of those things in this section. So everything we've looked at so far, we've always thought that there would be enough of both reactants to enable complete reaction. That is, at the end of the reaction, there won't be any of the reactants left over. All of the reactants will be completely exhausted. But more commonly, what we'll see is that one reactant will be used up before the others. And the reaction that runs out first will cause the reaction to stop. And it's called the limiting reactant, because once that guy runs out, it's game over. So you've probably, done this little experiment when you were in perhaps elementary school, and you light a candle and then you put a jar over it, and it goes out once all of the oxygen is burnt up, right? And it doesn't matter how big the candle is, it goes out once all the oxygen is burnt out, because the oxygen is the limiting reactant. So that's an important concept. Once the limiting reactant is consumed, everything stops, right? So the reactant that's consumed first is called the limiting reactant. It's called the limiting reactant because once that one's gone, nothing else can happen. So the limiting reactant is the reactant that yields the smallest amount of product. So if I have that little candle and I lit it in the atmosphere, it might burn for 4 hours, right? Now, if I take that same candle and put it under the jar, it might burn for, say, 4 seconds, right? So the candle could produce a total of 4 hours of light if there was an unlimited supply of oxygen. The candle and the oxygen together under the jar only burn for 4 seconds. What that means is that the oxygen is our limiting reactant. The candle is what we call our excess reactant. There's more of it present than what can be used up. It's what's left after the excess reactant has been consumed. So that's after the limiting reactant has been consumed. So that's some of the language, right? The reactant that runs out first and determines the amount of product we get is called the limiting reactant. The reactant where there's some left over is called the excess reactant. So, a good example of this is thinking about this in terms of hamburgers. If you've got 5 buns and 4 patties, what's the maximum number of hamburgers that you can make? Well, assuming you're going to use, 1 bun and 1 patty for every hamburger, and then obviously the maximum amount of hamburgers you can make is 4, because the patties are the limiting reactant and they're going to determine the yield. Your excess reactant is buns, and you'll have 1 bun left over, all right? So you always have some of the excess reactant left over. You always have 0 of your limiting reactant, and then you can have some product as well. So when a reaction completes, what do you have? You have 0 limiting reactant, you have some products, and you also have some of the excess reactant. Okay. So let's have a look at this reaction that we've seen previously. It's the combustion of methane, right? It says if 2 moles of methane is reacted with 1 mole of O2, what would be the limiting reactant? So how we have to figure it out is just pick a product, any product. You can look at both of them if you want. And then you say, well, what would happen if all of the methane got turned into products? 100% of it, right? So 2 moles of methane would make me 2 moles of CO2, and then it would make me twice as much water, so it would make me 4 moles of water. Okay, so that's how much I would get if all of the methane could be used up. What about if all of the oxygen was used up? Well, I've got 1 mole of oxygen, so that could give me half a mole of CO2, and then 1 mole of oxygen could give me 1 mole of water, because they're in a 1-to-1 mole ratio. So if all of my oxygen could be used up, I could get half a mole of CO2 and 1 mole of water. Now, what did we say? You can identify the limiting reactant because it is the one that produces the smallest amount of product. So it's pretty clear in this case that O2 is our limiting reactant because it produces the smallest yield. And so that's really easy. So what's actually going to happen when these things are reacted? What will happen is the reaction will occur until half a mole of CO2 is made and 1 mole of water is made. And at that point, you have no oxygen left and everything stops. So in addition to our half a mole of CO2 and our 1 mole of water, we'll also have left over some methane, right? And we know that if we've used up, for every mole of oxygen that we use up half a mole of methane. So we would have used up half a mole of methane in this case, okay? So if we had 2 moles to begin with, we would have ended up with 1.5 moles of methane left over. Yeah, so that's kind of interesting. Okay, so again, and we mentioned this previously, more commonly we're going to be given amounts in terms of grams of our reactants. So let's have a look at this. So in this case, they're saying if I have 16 grams of methane being reacted with 96 grams of O2, what is the limiting reactant? So I've got to do the same thing. Imagine what happens if all of this gets turned into products. Imagine what happens if all of this gets turned into products. Now, I said before that you actually, and I kind of let the cat out of the bag, you only need to consider one of the products. So just pick one and just consider just that one. Okay, so in this case, I'm just going to consider CO2. You have to make sure it's the same one that you're considering for both reactants. So if I turn all of my O2 into CO2, how many grams of CO2 would I get? So I'm just going to do a grams of A to grams of B. So I do grams of O2 multiplied by 1 on the molar mass of O2, multiplied by the appropriate mole ratio, which is 1 mole of CO2 for every 2 moles of O2. So at this point, I'm just going to make sure I'm not getting off the right track. Now I'm at moles of CO2, and then finally I just have to multiply by my molar mass. So multiply by my molar mass of CO2, which is 44.01 grams of CO2 per mole. So that leaves me with 66 grams of CO2. So I can't decide anything at this point, because I have to do the same calculation but for my 16 grams of methane. So 16 grams of methane times 1 on the molar mass of methane times by moles of CO2 over moles of methane, and then finally times by my molar mass of CO2. So again, a grams to grams conversion. So got to get good at your grams to grams. Cancelling out my units to make sure I'm on the right track, and sure enough, I'm left with grams of CO2. And if I use up all of my methane, I only make 44 grams of CO2. Well, it becomes obvious the reactant that produces the smallest yield is the limiting reactant. So methane is the limiting reactant in this case. So what's going to happen? I'm going to make 44 grams of CO2, at which point I will have consumed all of my methane, none of that is left, and the reaction will stop. Okay, so the maximum amount of CO2 I can make is 44 grams. And that kind of leads us into the next topic, which is what is the maximum amount of product that I can make from a given amount of reactants. That's what we call the theoretical yield. So the theoretical yield of a reaction is the amount of product that I can make if I use up all of the limiting reactant. So here's a simple example again. We've got 1 mole of methane being reacted with 3 moles of O2. What is the theoretical yield of H2O? So 1 mole of this guy could at most give me 2 moles of H2O, right? Okay. And then 3 moles of O2, because they're in a 1-to-1 ratio, 2-to-2 ratio, would give me 3 moles of H2O. So the maximum amount of H2O that I can make is 2 moles. The reason being because my methane is a limiting reactant. Once I've made 2 moles of water, I haven't got any more methane left and the whole reaction stops. So my theoretical yield is going to be 2 moles of water. Okay. So we'll just go through that again slowly. My 1 mole of methane makes 2 moles of water. My 3 moles of O2 makes 3 moles of water. 2 is clearly less than 3, so what that means is that my methane is my limiting reactant and my theoretical yield of water would be 2 moles. Now, it should be pointed out that sometimes the theoretical yield is not asked for with any particular units, in which case you can, it's completely appropriate to give the yield in terms of moles. Moles is the SI unit for amount, but often you'll be asked to give the yield in grams, and you should always make sure you go ahead and do that if that's what's asked for. So the actual yield, is what you get when you do the reaction. And as you know, that, reality doesn't always live up to the theoretical expectations. So in our situation, we're never going to be doing reactions. So that means for you that actual yields are always going to be given in the question. So you just have to read the question, and somewhere in the data there will be given the actual yield. So the actual yield is just what you get when you really do the reaction. So in this case it says when 1 mole of methane was reacted with 3 moles of O2, 13 grams of water was obtained. What is the actual yield? Well, hopefully it's apparent in this case that it was 13 grams. So the actual yield is not something that you calculate, it's something that you measure. We're not making measurements in this class, so that means that the actual yield must be given to you in one way or another. So an important idea is that of the theoretical yield. The theoretical yield is kind of a normalized yield. So if I just give you the grams, my yield might sound really impressive until you recognize that the theoretical yield was, very, very large. So for example, if I say, hey, I got 5 grams of product, you might think, yay, that's so much, but theoretically you were meant to get 5,000 grams of product. It's not so good. So to get around that sort of issue, to kind of normalize these yields, we'll most commonly calculate what's called the percent yield, which is where we take the actual yield, what we got when we did the experiment, divide that by the theoretical yield, what you get when all of the limiting reactant is used up, and then finally multiply it by 100. So in our example, we had 13 grams of water being produced when the experiment was done. That was the actual yield, divided by 36 grams of water, which was the theoretical yield, and then times by 100, and we got a 36% yield of the water. So normally it's also important to say what the product is that you're talking about. Okay, so let's put it all together and go the whole way through and do a big kids question where we have to actually go from the starting amounts of reactants all the way through to percent yield of a particular product. So it says when 16 grams of methane was reacted with 96 grams of O2, 13 grams of CO2 was obtained. So what we recognize is that this 13 grams here, this is our actual yield. And the product that we're going to be working with is carbon dioxide. So what we need to do is calculate how many grams of CO2 would I get if I used up all of my methane, how many grams of CO2 would I get if I used up all of my O2, and then see which of those two numbers is the smallest, and that'll be my theoretical yield. So in my first step of this process, I'm going to identify my limiting reactant, and at the same time, I'll be also working out what my theoretical yield is. So I've got to do 2 grams to grams reactions here. How much CO2 would I get if I turned all of my oxygen into CO2? And how much CO2 would I get if I turned all of my methane into CO2? And to do grams of A to grams of B, it's pretty easy. You do grams times by 1 on the molar mass of A, times by your mole ratio, times by your molar mass of your B. So 96 grams of O2 times by 1 on its molar mass, 1 on 32, and the grams of O2 cancels out, leaving me with moles of O2. Then I'm going to multiply by the appropriate mole ratio, 1 mole of CO2 for every 2 moles of O2, so that leaves me with moles of CO2. And then finally, to turn that into grams of CO2, I've got to multiply by the molar mass of CO2. So there we go there, leaving me with grams of CO2. So if all of my O2 is used up, I get 66 grams of CO2. I go through the same process with the methane. 16 grams of methane, multiplied by 1 on its molar mass gives me moles of methane. Then I'm going to multiply it by the appropriate mole ratio. I get 1 mole of CO2 for every 1 mole of CH4. Cancelling units gives me moles of CO2. And then finally I'm going to multiply by the molar mass of CO2, and that gives me grams of CO2. So I can see that my methane is my limiting reactant, and my theoretical yield is 44 grams of CO2, because that is the maximum amount I can produce, because once I've made that amount of CO2, all of my methane is gone. So now I'm ready to do my second step in this process, which is to calculate the percent yield. So to calculate the percent yield, as we know, it's the actual yield divided by the theoretical yield times by 100. So my actual yield was given to me in the problem, 13 grams of CO2. My theoretical yield, which was calculated, that was when all of the methane was consumed, 44 grams of CO2, and then times that by 100, and that gives me a 30% yield. And sometimes you're asked to say of what products are of CO2. Okay, so I hope you found that helpful. That's one of the foundational reaction calculations that we're going to be doing in chemistry, calculating a percent yield. Key to being successful in calculating a percent yield is being really good at doing the grams of A to grams of B calculations, because you're going to normally need to do at least 2 of those, and then having a good understanding of what we mean by limiting reactant and theoretical yield. If you've got those things down, then the rest is actually pretty mechanical. Okay, good luck with everything. Bye.